Okay, welcome back. So what you may have noticed in the last video is we didn't really talk about curvature of the hyperbolic plane. So let's do that now. So on the hyperbolic plane of radius rho, the area of a triangle is given by rho squared times pi minus alpha minus beta minus gamma. And so the hyperbolic plane, it doesn't matter which triangle I use, I'm always going to get the same answer for the curvature k. So the curvature of the hyperbolic plane is going to be equal then to, again, it's the holonomy of the triangle divided by the area of the triangle. And we get the exact same answers for the sphere except with a minus sign because this is the negative of what it was for the sphere. So we get negative 1 over rho squared. Okay, and so what we see is that the curvature is negative for a hyperbolic plane. It's 0 for the usual plane, the Euclidean plane, and it's positive for the sphere. And notice that on all these surfaces, on each of these surfaces, the curvature is constant. It doesn't actually depend on what triangle you draw. It doesn't depend on where you are on the surface. Okay, and that's one reason that when we're studying surfaces, we focus on things like the sphere, the plane, the hyperbolic plane in this class, is these are some of the most basic spaces, and one sense in which that's true is that their curvature is constant. So that leads to very nice descriptions of things. So for instance, here's a space that does not have constant curvature, and if I ask you what are all the geodesics on this thing, it's going to be a much harder question. It's going to be hard to solve. I think that was most of what I wanted to cover for today. So let me just end with a couple questions which you should take some time after I ask them to think of them on your own. And this involves maps. So a map is a way of, a map of a sphere is a way of projecting a sphere onto a plane, right? So the question is, can you project the sphere onto the plane in a way that doesn't have, so without distorting anything, in a way that preserves distances and angles, is what I mean. Okay, and I'm sure that some of you immediately realize that the answer is no. There's no way to project the sphere onto the plane without changing the distance between certain points. And if you've ever deflated a beach ball and flattened it on the plane, you see, well, yeah, of course things get squished, right? But a slightly harder question is, can you do this locally? Maybe I'll put that in a different color. Can I do this locally? In other words, can I project just a small region of the sphere onto the plane without distorting it. And you can ask the same thing about hyperbolic space. So we have this map of hyperbolic space. And the map maps the hyperbolic plane into the upper half plane. But as we've talked about a lot, there's distortion in this map, right? Distances are not preserved under this map. And so you could ask, well, is there a different map, a better map, that sends the hyperbolic plane onto part of the Euclidean plane without distorting anything? That would be great, right? That would make calculations a lot easier. And as you might guess, the answer is no, but you can ask the question locally. So I guess I'll just phrase it this way. What about if I just take a piece of the upper half plane, not the whole thing? Can I map that onto the plane? Or sorry, a piece of the hyperbolic plane. So what about a small region of the hyperbolic plane? Okay. So pause the video for a second and see if you can convince yourself that either A, this should be possible for some of these spaces, or B, it's never possible. Okay, now the answer to both these questions is no. Why is that? Well, think of some quantity that would be preserved by the map if the map didn't have distortions. So if there was some map that preserved angles and distances, then there should be some quantities that are preserved under that map. And can you think of any quantities that are not the same on the sphere and on the plane, even locally? And use that to argue that there does not exist any maps without distortions, because the quantities would have to be the same if such a map existed, but they're not the same. And I guess I'll just tell you the answer is curvature. Curvature is a local quantity that is not the same on the sphere or the plane, but if there was such a map, it would have to preserve the curvature at a point P, but the curvature is different, and so it's not preserved. So there is not such a map.